on outsourced computation and federated learning. The first talk is malicious secure peer almost for free, and Patrice will be giving the talk.
Hey. Oh, hi everyone. Thank you for coming to my talk. So yeah, I'll be talking about constructing maliciously secure PIR schemes. And this is joint work with my excellent co-authors, Brett and Matan. Okay, before talking about maliciously secure PIR, let's just recap what standard PIR does, or semi-honest PIR. So roughly, this is a protocol between a client and a server. The server holds some database, and the client wishes to retrieve the ith entry of the database in a private manner. Okay, so it will send its index I encoded or encrypted in some way, and the server will respond with the same with the ith entry, again under some kind of encoding. All right, and the server can then decode this encoding to get back. The client can decode this to get back db sub I. All right. The properties that we want from PIR at a high level are correctness. The client should get out dbi if everybody is following the protocol. Privacy, the server should not learn what index the client queried just by looking at its message, right? And finally, we also want efficiency, right? We want the communication and ideally the computation also to be small, sublinear in the size of the database. Okay, so this is a notion, beautiful notion, goes back, I guess, 20 years now. But most of the works in this space, they focused on the case of semi-honest servers. So they don't consider the case where the server can misbehave or deviate from the protocol. Okay? So let's see what happens when the server can act maliciously. Okay. All right. So the first attack we'll consider is what's called a selective failure attack. So to see this, how this works, let's consider a particular application. The server holds a database of public keys, encryption public keys, and the client wishes to retrieve one of these to send an encrypted message to their friend. Okay. What the server can do is try to speculatively replace the ith public key with some garbage, let's say all zeros. Now, if the client tries to retrieve the ith public key, it'll just get garbage and won't be able to send its encrypted message to the friend. But if it queries for another public key, let's say some other j not equal to I, then it can indeed retrieve a valid public key and send a message to the friend, right? If the server can observe this discrepancy, see, like in one case the message was sent and in another case there was no message, right? It can figure out, hey, maybe the client was indeed querying for location I. And so we've violated privacy for the client. Okay, so that's not all. You can also do other kinds of things. You can consider actually this attack was even noticed back in the earliest works in PIR. But the second kind of attack can happen when there's multiple clients interacting with the server. What the server can do is show to each client a different database or a different view of the database. Okay, so to client 1, it can show DB, and to client 2, it might show a different database, DB prime. And now, even if the clients retrieve the same location, they might, or ask the same query, they might get different answers back. Okay. All right. So we call this an incoherent view attack, and basically the point is that the clients disagree on what database they're interacting with. Okay. All right. So to resolve this, there's been a bunch of prior work in the last few years on constructing maliciously secure or authenticated PIR schemes, which I'll just call MPF for short. There's been a sequence of works in the past few years that try to solve this problem. Okay, and here the model slightly changes. Now there's an offline phase in which the server sends some kind of digest or commitment to the database, which is stored with the client. The client, along with this digest, can then, in an online phase, produce some kind of PIR query and get back some kind of response from the server. But now, instead of always having to output this dbi, the client is also allowed to abort by outputting bot. Okay. So there's some kind of the client can error out. So the properties, correctness is almost the same. If both the client and server are honest, then the client will indeed recover dbi. But where we start deviating is with privacy. Okay. What we want now is a stronger guarantee that the server should not learn any information about the client's index, even if it can see whether or not the client aborted. Okay. That information should not leak any information, anything about I. Okay. And this property intuitively kind of solves the selective failure attack, because even by inducing selective failures, the client will fail, right? But then that failure will not leak any information about what the index was. So this gets us past this selective failure attack. A new property that we want in this case is what's called coherence. Okay, so a query for the ith index should result in the client outputting either dbi or bot, not like any kind of intermediate third value like db prime I. Okay, and this naturally solves the incoherent views attack. Okay, and we want the same kind of efficiency goals as before. Okay, so this is the definition, high level, of Ampere. And as I said, there's been a sequence of works in the past few years that try to construct these kinds of Ampere schemes. Okay, so why aren't we done, right? Why am I giving this talk? And the point is that there's like these works have done produced lots of beautiful constructions, but unfortunately there's still some gaps left behind in the literature. The first is that kind of all of these constructions, how they work is by taking some pre-existing semi-honest PIR scheme and then modifying it in some kind of non-black box way to get some maliciously secure PIR scheme. Okay, so it's kind of there's no general recipe that I can just plug in any PIR and get out an Ampere scheme. As a corollary, the assumptions from which we know Ampere are also limited. Like whatever these constructions rely on, so like LWE, DDH, blah, 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 that's the only assumptions, those are the only assumptions from which we know Ampere. Okay, so ideally we'd like to, but I guess the gap here is that we know of PIR schemes from many, many different assumptions, for example, quadratic residuosity. Okay, and finally, as a third corollary, like all of the underlying PIR schemes, they achieve square root communication complexity. And this communication complexity is inherited by these Ampere schemes. But we also know of excellent PIR schemes which achieve polylogarithmic communication complexity. So for example, the doubly efficient PIR of LMW. Okay. So to solve this, I guess that's what we did in this work. We constructed, we first provide a new compiler which lifts any PIR scheme into an Ampere scheme. Okay, it takes 3 ingredients, some base semi-honest PIR, a vector commitment, and locally decodable code. I'll explain what these last 2 things are, and gives you a Ampere scheme with some arbitrary n to the epsilon overhead. Okay, so this resolves the first concern. Now we have a general recipe which takes you from PIR to Ampere. Okay, also kind of resolves the second issue because we're able to show that PIR and Ampere are equivalent in terms of assumptions. This is because you can construct collision-resistant hashes and hence vector commitments from PIR. Okay, so kind of this means that if I give you a PIR, or if you give me a PIR, I can give you an Ampere with the same assumptions. Nothing additional necessary. Okay. And finally, we're able to resolve this efficiency conundrum by showing the modification of a slight modification of our compiler can be applied to the doubly efficient plain PIR scheme to get doubly efficient Ampere. Okay. All right, so that was a lot of words. Any questions? No? Okay, so this is just a summary of what I just said, but now comparing with the prior works. As you can see, we improve on basically all of the fronts. Okay, all right. So there's no questions, then I'll start talking about how we actually achieve this result. Okay. So I'll first introduce this new primitive called vector commitments. This basically allows the committer to commit to some database or message, and then provide some kind of opening proof that asserts that the ith location is some claimed value. Okay. The properties we want are completeness. So if the committer is behaving honestly, it can produce valid proofs that the client will accept. Soundness or function binding or position binding, which says that you cannot provide different openings that are accepted by the client for the same location. So I can't give you a proof for dBi and also for dBi prime. Okay, there's no way to do that. And finally, efficiency, which just says that the digest and the proof should both be much smaller than the database. Okay, you can just think of here of like Merkle trees. Merkle trees, the batch size is just 1 hash, and the proof size is logarithmic in the database. Okay, all right. So let's try to immediately just use this to try to construct MPeer. And the construction is simple. Okay, so when I want to get a digest of the database, I'll just use the vector commitment to the database, and this will be my digest. And then in the online phase, instead of replying to PIR queries with respect to the original database, the server will construct an augmented database where alongside each entry, I store the opening proof. Okay, so I store db1, pi1, db2, pi2, and so on and so forth. And now when the client requests the ith entry, it'll use the underlying plain PIR to query for the ith entry. But now instead of just receiving the database entry, it'll also get the corresponding opening proof. Okay. It'll invoke the PIR decoder to get out dbi and pi. But before producing its output, it'll check the opening proof, and if it's valid, it will output dbi. If it's invalid, it'll just output bot. It'll error out. Okay. So correctness. So actually, this simple construction already gives us coherence, right? There's no way for the server to cheat because the position binding means that I can't open the same location to multiple values. We get efficiency because I can just think of Merkle trees. There's not really much overhead induced in this construction. But unfortunately, we don't get privacy. Okay, it's kind of straightforward to see that the selective failure attack that we saw before also just carries over here. We just have to tweak one of the proofs, and if the client retrieves that location, you'll still get an invalid proof, and you'll error out, but only selectively. Okay, and kind of the high level for why this happens is because the errors are kind of too localized, right? And the server is able to malleate only the ith location without affecting any of the others. Okay, and what we want to do intuitively is kind of spread out this error all over the database. So if the server tries to corrupt location 1, it'll corrupt a significant fraction of the entire database. Okay, so to do this, or to fix this, what we're going to do is we're going to use a standard tool in cryptography, or I guess in computer science, called error correcting codes. And we'll use one particular variant called locally decodable codes. Okay. So locally decodable codes are just basically like error correcting codes, but they have a special property that if I want to get the ith message symbol, I don't have to read the entire code word, but can get away with reading only a very tiny fraction of the code word. So like, let's say 1 over square root n. Okay. Okay, so in a little bit more detail, a locally decodable code, just like a standard error correcting code, allows you to take your message and produce some kind of code word, which is a constant times larger. But the interesting property, again, is local decoding, which says that for any index, I can invoke this LDC query algorithm. It'll give me some set of queries to read from the code word. And the property that LDC satisfies is that as long as there's not too many corruptions, let's say less than a 1/3 fraction of corruptions, then for any index I, if I read these locations, so I get like E sub q, then I can use those to decode dbi with very high probability, 2/3. Okay, and you can amplify this as you want by just making more queries. Okay. All right, so this is the high-level property that we care about for LDCs. I'll try to be a little bit faster because I think I'm going to run out of time. Another property which we'll use later on is called smoothness, which basically says that if I look at any of these query sets, any individual query in this in Q is going to be kind of uniformly distributed. It is independent of I. Okay. So we will leverage these 2 properties in our construction eventually. Okay. So this is background on LDCs. Let's see how we can use these to get around the error that we had before. Okay. So the template will look exactly the same, except now instead of committing to the original database, the server will commit to this encoded database. Okay. So the vector commitment is over the encoding. And now in the online phase, to make a query, instead of directly querying for location I, the client will invoke the LDC query algorithm, get some query sets, and make PIR queries just for those queries. Okay. So it'll retrieve those code word symbols along with their opening proofs. And again, now here's a new deviation from the previous construction. If any of these proofs are invalid, instead of immediately rejecting or aborting, we will take the responses and just erase those invalid locations. Okay, we'll just pretend like we don't have values there. Okay, and then we will invoke the LDC decoder on this partially erased response. Okay. Okay, so this is and then hopefully this will give us DBI. Okay. So any questions about this construction? Does it roughly make sense? Okay. I see some nods, maybe. But all right. Okay, so this preserves correctness. If the server behaves honestly, then the decoder will succeed. There won't be any invalid proofs. So we're good. It also preserves coherence because the LDC decoder it either outputs the message symbol or it outputs bot. It doesn't give you some kind of intermediate result. Okay, and it also gives us good efficiency because we know LDCs that get like n to the epsilon query complexity. Okay, so now we're incurring an n to the epsilon multiplicative overhead over the underlying PIR, but you can drive this epsilon down as much as you want, essentially. Okay, all right, so I promised this would improve upon privacy, so let's try to take a look and at the privacy of this construction, and we'll focus on one particular LDC, namely this Reed-Muller LDC. Okay, so to encode a Reed-Muller code word, okay, we'll consider the bivariate case. You can generalize to multivariate. Bivariate is easier because I can draw a square. Difficult to draw a cube. Okay, so to encode some database DB, what you're going to do is you're going to interpolate a bivariate polynomial that agrees with the database on some subset of your field. Okay, your encoding will just be the evaluations of this bivariate polynomial everywhere in the field at every point. Okay, and you can choose your field small enough so this actually works out. Okay, so that's encoding. That's standard. Local decoding works as follows. So what we're going to do is if you want to retrieve DBJ, we're going to pick a random line that passes through the jth location. Okay, so it'll look kind of like this. This is a funky line because we're working mod P, so things wrap around, but it's still a line. Okay, so we'll pick a random line, and the thing I guess that people have noticed about Reed-Muller LDC, this is not something I'm coming up with right now, is that if you look at the code word symbols along this line, they are the evaluations of some kind of univariate polynomial. Okay, and evaluations of a univariate polynomial are precisely another famous code called Reed-Solomon code. And you can then just invoke the Reed-Solomon decoder on this line to retrieve DBJ. Okay, so the nice thing about this is that this actually works. I won't analyze it, but people have done so. And it has good efficiency. To retrieve DBJ, instead of reading the entire code word, I only have to read just square root many elements or many code word symbols. Okay, so that was like a lot of background. Let's try to see what happens if you plug this LDC into our construction. Okay. Unfortunately, it turns out there's an attack. And what happens here is that if the server wants to induce a selective failure when you're trying to decode for I, what it will do is it'll pick some line through I and corrupt all of the points on that line. Okay. This is still only a, I guess, sub-constant fraction because this line is square root many points, right? But unfortunately, it'll be the case that when the client queries for I, it will query this line with some non-negligible probability. There's only like so many lines which pass through I, and this line will be picked with 1 over poly probability. Okay. On the other hand, if the client tries to query for j not equal to I, so some other point, so let's say this line, right? It will only encounter one corrupted point on that line. So it was like this one, that red corner, that becomes blue, that will be corrupted, right? But because we're getting a Reed-Solomon code word, this should still successfully decode, right? It can tolerate some errors. Okay, so this leads to a selective failure attack still. And this is because even though, for both I and j, you will succeed on average with good probability, the success probability can differ between the two, right? as long as it's above like your whatever lower bound is, to like 2/3 is what we said, right? You're fine according to the definition of LDCs, but it's not good enough for our purposes here. Okay. So what we're going to do is, I'll skip through this slide a little bit quickly, is instead of trying to just always repair, we're going to try to detect whenever there's a corruption in the code word. Okay. So we're going to modify our query procedure, and now when we want to query for J, we will query a line, but also some test points. Actually, here we're saying multiple lines because I've done this amplification to bring the failure probability down to negligible. But we're going to query some lines, and we're also going to query some arbitrary, independent, uniform test points. Okay. And we're going to query for both the lines and the test points. Okay. So now the decoder will try to use these test points to figure out, has the code word been corrupted or not. If it sees that there's any corruptions on these test locations, it'll immediately abort. Otherwise, it'll try to decode using the lines that it got. Okay. And the idea is that the server can't introduce too many errors now because it'll be detected by the test point. Okay. That's the intuition. Unfortunately, we can't actually prove this private. Okay. And this is because, I guess, of a kind of a funny thing which happens when you try to do PIR with information theoretic things. And the issue is that PIR doesn't actually give us this guarantee that the responses to the test queries are independent of the LDC decoding queries. Okay, there's no PIR does not give us a guarantee that these responses are completely independent. Okay, and it turns out that the adversary, at least in theory, could, in some sense, use this. All PIR guarantees us is that the server learns nothing about the query responses, but it's possible in some way that the server could try to correlate the responses with each other, right, in some kind of funky way.
1 minute.
1 minute. Okay. All right. So yeah, so essentially this allows the adversary, at least in theory, to make some kind of attack which violates privacy. So we're not able to prove this strategy is secure. And what we do to work around this is to change how we sample the test points. So instead of sampling the test points completely uniformly at random, independent of our query location, we're going to sample the points by taking them from the lines that we're already querying. Okay, so let's say this is the line that I want to query. That point T will be some random point on that line, and I'll do this for each of the lines that I want to query. And otherwise, it's the same as before. Okay, so plugging this into our construction, the reason why this works, we'll go a little bit quickly, is that essentially it comes from smoothness, right? Like each of these test points by smoothness is kind of uniformly distributed in the entire code word. So it's in particular completely uncorrelated with the query index that we're trying to make. So it cannot leak any information about what index is being queried. Okay, that's a high level takeaway. I guess I don't have time to go into the details. But otherwise the construction just works with this small tweak, okay? So conclusion, we had this PIR compiler, which takes you from PIR to maliciously secure PIR. It achieves great efficiency. There are a few open questions. Can we reduce this multiplicative overhead instead of being, if you want negligible error, then can you go to additive overhead? And also, can we implement this with actually concretely efficient LDCs? Okay. Yeah, so that's it. Thank you. The paper is on EPUB. Do we have time for questions?
Yeah, we have time for like one very quick question.
Maybe I give an exceptional.
I'll be quick. It seems like this general paradigm of like MVC with authenticated inputs is happening in a lot of different functionalities. Like you see this in PSI as well. What are the like real world needs for this for your case? I'm guessing this is something like the peer server is like some big service that like Apple or Google or something is running, and there's some concern about the database being like consistent throughout inputs.
Yeah, the inconsistency attack. If you're thinking of like the public key encryption thing that I mentioned, it could be that I don't know, you're running some kind of key, so the There's a server which is running the key, I guess, which has this key database and is also running the messaging service itself. So let's say Signal, right? So then you might leak whether or not you're engaging in, or who you're talking to, things of that sort. Maybe in like an anonymous communication system. There's also, I guess, applications to, like wherever I guess you apply PIR, there's no reason to assume that the server would be semi-honest. If there's like an easy attack, an undetectable attack by which it can deviate from the, and learn information about the client's index. So
Okay, thanks, I appreciate it.
Yep, let's thank the speaker again. All right, so next up we have That's Amore, amortized efficiency for pairing delegation. And this talk will be given by both Adrian and Elena.
Thank you, Steve, for the introduction. Thank you, guys, for coming to this session. I'll tell you a little something about this lovely line of work on amortized efficiency for pairing delegation. So first of all, what are pairings? This is just one slide. So if you know it, don't worry. If you don't know it, I will just introduce introduction, the notation. So pairings are bilinear maps on groups that are defined as subgroups of elliptic curves. So it's going to take points from one group, G1, and another point from another group and pair them together to create a target point in another group. And here we can see that we use the additive notation for the base groups. So we take a scalar multiple of the generator P of G1 and the multiplicative notation. So we exponentiate on the target group. Okay, pairings in cryptography, they do magic. Right? If you haven't seen it, this is a very abridged list of references. We can do one round tripartite Diffie-Hellman key agreement. We can do short signatures. We can do a fuzzy identity-based encryption. And most recently, like hints, which is a threshold signature with silent setup. So they are amazing. What's the catch? I will show you the computational cost in clock cycles in 10 to the take clock cycle on the BLS 12381 curve, which is used in Zcash, Ethereum, and Chia. So this is the cost of doing scalar multiplication in G1, and the height of the rectangle is proportional to the cost. To move and do operation in G2, we kind of double the costs on this curve, and we can see that the trend is different from curve to curve, but this is the overall trend anyway. To do our exponentiation by a random element in GT, we go up again, but compare this to the cost of computing a pairing. We're talking about an order of magnitude difference. And while this is still considered efficient, it actually is intractable, so prohibitive. It cannot run on the weaker IoT devices that we have right now, including like hardware wallets that you plug into your computer to sign your transaction, but maybe you also want to verify that your Zcash is correct, that the transaction that you want to sign so far are correct. This you cannot do. So what do you do when you cannot do things yourself in cryptography? You delegate to someone else. And in this case, since 2005, we have the idea of pairing delegation protocols, where a computationally restricted client is talking to a computationally powerful server who we don't trust, but we want to do them to do some operation. With some notation, we're going to have inputs A and B, the pairs to input to the pairing, or a batch of pairs, so a set of pairings that come all together, pairing inputs. And after talking to the server, the client should be able to output some points in GT, and it better be the case that these points are actually the evaluation of the bilinear map. So that's where the verification is. Like I want to verify that the server is actually returning not random points, but the correct one. If the server can fool me and make me accept any point, then the protocol is not secure, it's broken. And so far, the tradition has been that the client does a little bit of precomputation and does one delegation or delegates things in a batch. And then the next time he needs to delegate something because it's attaching the hardware wallet again and checking the state of the chain so far, then it will run again a precomputation step and do another delegation. This is just to give an intuition, like starting a match every time you want to light a candle. What's the state of the art? Well, we have a category 1 of schemes that are very efficient, lightweight, but they are broken. So if you try to cheat too much on what kind of operation you can relieve the client from doing, you end up that a server can fool you easily. And in particular, in this paper, we present attacks to 2 recent work on pairing delegation that we break. The other category gets unconditional security, good, in this one-shot framework that I show you with the match and the light. But they are usually computationally heavy, meaning that either are completely inefficient for pairing delegation, so the clients need to do more computation than pairings, or even compute pairing locally in order to outsource a pairing, or they achieve some efficiency, but only in special settings, so not overall. So what is wanted still is a pairing delegation protocol that is reasonably secure for some model and efficient. And guess what? That's what we do. How do we do it? We move away from this one-shot framework to a sequential framework. So we're going to ask the client still to start a match, so to do some precomputation, but then use this precomputation to light several candles at once, not just one at a time. Then we notice that we don't necessarily need unconditional security, which is security no matter what forever, but everlasting is enough. I need security as long as my protocol is running. So once the last candle is off, even if you know the secret coin that I used in my delegation, doesn't matter. I got the pairing value that I wanted to have. Now you can no longer cheat. So this is an observation that was nowhere in this part of the literature. And finally, in addition, we also move away from oddly powerful adversaries to realistic one. What do I mean here is that we could provide unconditionally secure pairing delegation, but when you have a pairing, you usually rely on the Diffie-Hellman assumption, discrete log, some other kind of group-based assumption. So you need anyway an adversary that is computationally bounded, but then you can have a delegation that is unconditionally secure. So we kind of match these two things and restrict the adversary in a meaningful way that Adrian will walk you through with the details, so that these two things become more reasonable. And we also introduce a new security assumption that is bound to our new proof technique. Finally, an overview of our results. First of all, we provide an impossibility result that is inspired by the new attacks that we found. And essentially, this says that for all the way that we know to produce a secure verifiable delegation scheme for pairings, the client needs to start a match. The client needs to do some precomputation, and this needs to involve the GT operation. So they will be a bit expensive. So the best you can do is to have a framework for leveraging. I'm going to do heavy computation once, but then I will reuse it several times. And this is the idea of sequential delegation. Finally, we presented the Amore protocol that achieves amortized efficiency. We have a novel proof technique connected to our new assumption. And we also do experimental evaluations and show that we actually achieve efficiency. On the way to achieve this, we also introduce an efficient short scalar sampling trick. And now I will leave the floor to Adrian that will walk you through the technical part.
Thank you very much. Yes, so on the second part of the presentation, I'll just walk you through an overview of our construction, then a bit of the security analysis, and finally some of the benchmarks that we obtain in the paper. Oh, sorry. There we go. So in our construction, the client first starts with this pre-computation phase or one-time setup, because it's done only once to make several delegations. And it performs some operations in GT, mainly an exponentiation in GT, and it starts the time counter, which will be useful later to prove this everlasting security that Elena described. So once the client has a hold of the pairing inputs that it wants to delegate, it starts a new phase, the setup phase, and it samples some secret scalars from a bounded set of the full range, the multiplicative group set Q star. And notice this, this efficiency parameter, phi. So the smaller phi is, the more efficiency we obtain, because it becomes cheaper later on to construct the public view and also to verify. And notice that J runs from 1 to the length of the inputs that we're delegating. So we can delegate maybe 3 inputs, like in graph 16. And yeah, so in that case, we would have J from 1 to 3. So the client constructs the public view with a probabilistic routine using these pairing inputs and also these secret scalars, and sends these elements to the server. The server makes the following computations. It computes the pairing evaluations and also an element on GT. They'll be used later for the client to verify the correctness of the pairings received. So besides that, the client also verifies that the time has not exceeded a certain threshold. This is the latency parameter that we use. And notice how the adversary can only cheat from the moment it receives the public view to the moment it sends back the output. And therefore, if the adversary cannot cheat in that period of time, then it can't cheat afterwards, right? So that's why we have this notion of everlasting security. I'll talk a little bit more afterwards. And finally, if the client, if this time check passes and the client later in time has some new inputs that it wants to delegate, it can go directly to the setup phase instead of starting a new match on the one-time setup. So this helps with our notion of amortized efficiency. So as Elena mentioned, the adversary doesn't necessarily need to be honest. It can, the server, it can be malicious, it could try to cheat. And we are interested in measuring this probability, the probability of the adversary given the public view that it receives, the probability of it outputting something different than the honest output and passing the verification phase. We prove in the paper that this is equivalent to the adversary in extracting one of the secret scholars or guessing it if it's completely masked. Yes, so this is simply an overview. So there's two different ways we can approach our construction. We can make it unconditional, but this requires expensive computations to construct the public bundle, the public view, because it needs to mask all the secret scholars in order to obtain unconditional security, right? So this way, the only way the server can win is by guessing one of the randomly guessing one of the secret scholars. On the other hand, we can bound the adversary in time, as I showed before with this time parameter, which allows us to allows the client to construct the public bundle in a cheaper way, but makes the secret scholars extractable after X computations. So how do we bound the adversary? In our paper, we bound the computational resources of the adversary to the entire Bitcoin network. And this is pretty convenient because the Bitcoin network capabilities are updated after every single Bitcoin block with the hash rate, which as of the time of the writing of this paper is a staggering 2 to the 70 hashes per second. And not only that, under the fair assumption that computing the hash of a Bitcoin block header is significantly cheaper than computing any short scalar multiplication in any of the bilinear groups, we can also make this upper bound. Yeah, so basically we can, the time bound is the number of computations, the number of short scalar multiplications that the adversary can perform within a certain interval of time. A little bit on the security analysis. This is a very simple example just to understand the core idea of our security proof. So suppose you have an additive group, which is cyclic and of prime order Q. And suppose you sample an element from the multiplicative group, say Q star, which spans the whole group whenever you make a scalar multiplication on the generator. And then consider these two cases when you have two secret coins, R1 and R2, sample from the full range. And when you sample these two secrets from a bounded range of ZQ star. And let's suppose just for a moment that this is the public view. This form, of course, in our construction is something more complex, but this is enough to understand the security idea. So on the left side, if R1 and R2 are sampled from the whole range, when the server gets this public view, since it's two equations, three unknowns, they're unbounded, there's Q minus 1 equiprobable secret tuples that yield this public view. So we automatically get unconditional security. But as we said before, the larger phi is, so if we sample from the whole group, it becomes more expensive. But if we want to be cheap on the other side, if we restrict R1 and R2 to a bounded set, notice how in the public view, psi is expressible, can be expressible in terms of R1 on the first equation and R2 on the second one. So these expressions here are basically expressing psi in function of R1 and R2. So the adversary can run this intersection set, and when 2 to the phi is significantly smaller than ZQ star, this intersection most likely will only contain Xi. And therefore, the server may extract the secret tuple within up to 2 to the 5 plus 1 scalar computations NG. As you notice, the only difference between these two cases are where we're sampling the secrets from. One is the full range, the other one is a bounded range. Our security, and this is where our security assumption lies. It's not, we can't really like prove formally that this is like, you know, like the best way that, the best attack that the adversary can do. But in the paper, we argue that this problem is essentially the same as breaking the double key expansion of a block cipher, which is most efficiently done by Diffie-Hellman's meet in the middle attack. And this was back in the 70s or 80s, whenever. And there hasn't been any better attack yet. So we kind of make that comparison. And this is basically our assumption that adversary can only, the most efficient way the adversary can win is in this way. So if the adversary is bounded in making a certain number of computations, we can actually bound its probability of winning, its probability of cheating, sending to the client something that is not the pairing inputs and passing the verification phase. So as I mentioned, this would be its best strategy. It would have to sample, it would have to choose elements from this bounded set such that their sum doesn't exceed this computational limits and intersect the generated sets and hope for a non-empty intersection. And we get this chain of inequalities. Of course, the probability of Xi belonging to intersection is the same as the probability that the adversary chooses subsets S1 and S2 such that they contain their corresponding secrets R1 and R2. And then the paper is a little piece of math by introducing a new parameter, sigma, which stands for the statistical parameter, which together with the other parameters in this work, if they satisfy this relation, then we get this upper bound. So we can tweak the statistical the probability of the adversary and retrieving any of the secrets and therefore forging a pairing in our construction. So for our benchmarks, we set these parameters, tau equals 1 second, which yields kappa equals 70. So the adversary cannot compute more than 2 to the power of 70 short scalar multiplications per second. We settle for 40 bits of statistical security, which yields according to this formula underneath phi equals 90. And finally, this is not result overview, but efficiency results overview. So basically the benchmarks for the curve BLS 12381 that is widely used, as Elena mentioned. We noticed that previous work for delegating a single parent doesn't obtain efficiency. As you can see here, we have a factor larger than 1 times the cost of computing a pairing. Having unconditional security. In our case, with everlasting security, we obtain efficiency. We obtain 0.68 times the cost of a pairing. So mission accomplished. And for a larger batch, for delegating batches of 3 pairings, for example, for verifying transactions on using on Zcash or running growth 16, we obtain even more efficiency. And this is for sequentially delegating 10 delegations. Yes, if for more information, please check our paper. Thank you very much. Oh, questions?
Are there any questions of the speakers?
So this is still designated verifier, right? There's not anything you can do for this public verification. My application is in recursive verification of snarks. If you can make the like designing a circuit for checking pairings cheaper than just doing the pairing.
So for future work, we're thinking of making, working on doing a public, publicly verifiable. But right now is so that everybody can verify it. But right now it's only the client. So it's we leave that for future work. But it's a very good question. Yeah, that's follow-up work. Thank you.
Right, let's thank the speakers again.
Okay, I guess I'm starting.
So-
Welcome to this
So
soft
this
merge.
introduce you real quick. This is yeah, no problem. This is a combined paper, combined presentation. We have OPA, one-shot private aggregation with a single client interaction and its applications to federated learning, along with Willow, secure aggregation with one-shot clients. And this will be a joint talk given by Harish and Philip.
I just wanted to get to lunch fast, so let's get this party started. So Thus was born. It was a soft merge. We call it Willopa. I really wanted to bring plates from the dining room, and when I say Opa, break it, but they didn't let me take it out, unfortunately. They're very mean at the dining commons. But anyway, this is what happened. We had Willow, we had Opa, we've been playing around tag team. It was a roast battle at some point, and then at Crypto, we merged. So this is going to be the outline. I'm going to introduce the background, and then Philip is going to come in with talking about the one-shot aggregation and what really is one-shot. And then he'll describe Willow, and I'll end with OPA. Again, break a plate. So what is secure aggregation protocol? It's the setting where in a single server, I have a really powerful server that wants to get some data from its clients. The clients are weak, and so that's the motivation for federated learning. And it's pretty much, we've all used it. Gboard, Apple, I guess, also use it. But that's the idea where I want the central server wants to really train on data that's held by the client. And it was sort of conceived this idea that if the server doesn't see the data, it should be private, you know? Like most machine learning people, you sort of have this heuristic approach, think it works, it doesn't. And that's what they did, they broke it. So there's been so many attacks that says that even if I end up leaking information, sending just the model updates, there is a lot of leakage that's happening. So thus was born secure aggregation, where the idea is that you really want, you really want the server to only get the aggregate, the average, the sum. That's all it needs to actually do this training. And it seems to be a better heuristic and hedge than a very hard hoc saying, oh, if the server doesn't see it, it's never going to be broken. But clearly, no. Anyway, so that brings us to the properties of secure aggregation. You really want this malicious server, security against a malicious server where it can collude with a lot of clients. And what the server gets is nothing more than the output, which is the functionality, which is the sum here. And you want correctness where the server actually gets either the sum of the inputs or it can abort. And you really want to support this malicious client dropping certain honest clients. Say it doesn't like the client, it's going to drop the inputs, and you still want the security to hold. And there are two things that we don't really discuss in our work. Is this idea of the spurious inputs, where we say that, you know, well, a client can really screw up the aggregation by sending something that it's not really valid, right? And there's been a long line of work, both from the machine learning community saying, well, you can sort of be clever about it by modifying the aggregation approach, or there's work like Acorn and Armadillo, which is going to be in CCS this year, where we talk about, well, I want to catch these clients that send incorrect input. So I really want to try see that, prove the clients will have to prove that there's some L2 or L infinity norm bound that's being verified. Or Sybil attacks, which is when a server actually corrupts all but say, it can corrupt n-1 clients, in which case it really does get the one input alone of the honest client. So this is Sybil attacks. Neither of these are really germane to our protocol, even though, so yeah, let me just leave it at that. So what is the prior works? As you can tell, this is where the merge happened. We went from one template to another. So bear with me. Okay, so the first work that said this can be done practically for federated learning was this work by Bonowitz et al., where the clients essentially secret shared some masks with all the other clients. And the idea was that, well, I might drop out, right? You really need the ability for a mobile phone being like, I really don't have the battery to send inputs. I don't have a battery or the power to actually run a machine learning model right now. So you want to be dropout resilient. So the idea is that when a client drops, the other clients will pick up the slack and say, help recover the masks. And that what really happens is that now, because these clients really have to be online for multiple rounds, it's not really desirable. Bell et al. Improved on it, said, well, you can be slightly cleverer. We don't need to share with all of the clients. We'll only share with some kind of a neighborhood, so O of log and Brown. So you get some better asymptotics, but again, the rounds still is a problem. Then there was this old work by Elaine, where it said, you know, this is in a completely different setting, but that was sort of the first work that made this idea that private stream aggregation work, but you can't really have dropouts there. But the cleverness is that the mask will always sum up to 0, and you can really reuse this masks across multiple rounds. And then Ma et al. Sort of built on the idea of, this was Flamingo, but built on the idea of the CCS20 paper, but said, let me assume there is a designated committee, and I will only share with the committee. This committee can be reused across multiple rounds, so at least you get some kind of a reuse of the masks. And the idea is this is what we call as a representative democracy versus total democracy. Well, whether it works or not in the democracy context is a different story altogether. But the idea is that now I can reuse the committee for multiple rounds. Tough crowd. My jokes are not landing at all. Well, this is my soft launching my stand-up career. If you like it, write on Netflix. If you don't like it, still write on Netflix. Then Microsec actually came in and said, I will have a setup that's being reused across perpetuity. But the sharing of the key is very similar to what was earlier done in the C2 CCS works. Okay. Now this leaves us with the punchline, which is this work should be Asia Cup 2024, where they assume that, let me assume that every client who wants to participate will come in, will secret share its masks with this entire committee. So what really happens consequently is that you really need a very, very large committee because it's done by every client, but you really get both of the properties that you really want, which is the one shot in the setup phase and one shot in the masking phase. So the client behavior or participation is strictly restricted to 1 rounds. And that brings us to.
Thanks for the intro. This one. Yeah, so I'm gonna give an overview of now how can we build secure aggregation with these one-shot properties that we want. Wrong direction. Yeah. There we go. So we saw in the prior works, like a lot of the approaches are based on secret sharing, so masking. Basically, the clients somehow mask their inputs with a with a randomly generated mask or a seed, and then that somehow needs to be handed off to a committee. So one thing, one idea you could have is why not just use homomorphic encryption, right? So a natural baseline could be taking additive homomorphic encryption. The client, instead of masking, it encrypts additively using this crypto system. And then the committee just performs the decryption once the server has aggregated all the client ciphertext. So the problem here now is that if we have really long inputs within the federated learning use case, we will, then this committee will do a lot of work, right? So we would like to avoid this high communication on the committee side. So let's maybe make this more clear. So what are actually the things we want from a efficient one-shot secure aggregation protocol? Well, one is this one-shot property. We want no synchronization point between clients. And in fact, we want clients to be able to appear and disappear like no matter what. So we don't even want like fixed identities for clients. The second one is we want committee members to have low computation and communication. And that means that it should be sublinear in both the length of the vectors and the number of clients. And finally, we want security against malicious servers. And getting all of those together is basically what both of our papers are about. So first of all, one thought you might have is this even achievable, right? So we have all these nice things that we would like to have. Can we even get them? And it turns out, like in the standard model, actually we cannot. Because in the Willow paper, we have a proof that if we assume one-way functions and if we have some tolerated amount of dropouts, so we're not actually aggregating all the clients or none of the clients, then we cannot prove in the standard model that the protocol can be securely instantiated. The reason for that is like a very technical simulation proof-based reason, which is that the amount of communication that goes into the server after they have decided which clients will drop out is sublinear in the size of the output. So now if the simulator needs to fix the output in order to account for the sum of the honest clients that will be in the real world, that is not possible because we just don't have enough data that we can send from the simulator. So with a random oracle, we can actually fix that by just reprogramming the random oracle. But without that ability, we cannot have a security proof here. So, okay, so now that we know it's possible, we just need a random oracle. Let's see how can we construct it. I'll get back to the random oracle in a bit. But yeah, the main idea that was present in Acorn, but also in both of our papers, is to reduce the, instead of using this additively homomorphic encryption and then having the committee decrypt these long vectors, we instead do a hybrid kind of encryption scheme. So we use a key homomorphic, additive homomorphic encryption scheme and encrypt our long vectors using that. And then we use the committee only to decrypt the symmetric keys that are used to encrypt these long vectors. So a bit more formal, the client encrypts, samples a random key for the symmetric encryption scheme, encrypts the long vector using that key, and then encrypts the key using a separate encryption scheme. The server sums up all the encryptions of the vectors. And again, these are homomorphic in both the values and the keys. And then the committee has to decrypt just the sum of keys, and the sum of keys will then decrypt the sum of vectors. So the main differences between our papers is, first of all, how do we implement this KAG? So there are several instantiations that you can think of. In Willow, we have one of hint learning with errors, but then in OPA, Harish will present several other ones. And then the other question is, how do we implement this encryption scheme that the committee uses in order to decrypt the sum of KAG keys? And there are two approaches. One is we use the AHE scheme that would be the naive approach we had before. And the other one would be some combination of secret sharing and just regular public key encryption. Okay, so let me dive into what we do in the Willow paper. Here, this encryption scheme that is used at the committee in order to decrypt the KHE keys is in fact just additively homomorphic encryption. So this enc star and dec star here we replace by, well, first the key generation protocol and then an additively homomorphic encryption and decryption. The nice property about that is that the encryptions of keys, so these BIs here, can be summed up by the server. So the amount of communication that goes into the committee in total is independent of the number of clients. One issue that we have with this approach is something that we call the correlated ciphertext attack. So if we just implemented what we have here in the simplified protocol, then what a server colluding with a malicious client could do is look at all the ciphertexts that come in and then choose a target client and subtract all of the other client ciphertext from the target client and create that as a new client, right? So if we do that, all those will cancel out, and what we have as the sum will be just that target client's key, and that allows them to decrypt that target client's vector. So we don't want to allow that, of course. And in order to fix that, we require the clients to provide a proof of knowledge that they actually know what they're encrypting. So that fixes this problem, because now you cannot just mangle two client ciphertexts together in order to get another one. So now the remaining question is, how do we implement this committee, right? So far, we've been talking about this decryptor role that just takes a key and takes a ciphertext and decrypts it, but how do we do that in practice? And for that, we have a distributed key generation protocol that is robust to dropouts. So it's like a threshold encryption scheme. And if some of the committee members drop out, their secret keys can be recovered and we can still decrypt. And similar, the decryption phase is also implemented by separately doing a partial decryption on the ciphertext, and then just the server can combine these partial decryptions to get the final decryption output. So there's no communication in particular in the decryption step. It's only needed for dropout recovery. Yes, and then additionally, we also need zero knowledge proofs for the key generation and for the partial decryption. And similar to the client proofs, we implement those based on bullet proofs. So we just reduce the problem to inner product proofs, and that we implement using bullet proofs. Okay, now the remaining step is, how do we get malicious servers, right? So everything so far has been semi-honest server colluding with a malicious client. So how do we get security against malicious servers? And here, what can a malicious server even do, right? So that's the first question to ask. And one is, of course, we can take a client, multiply it, and then just aggregate 1,000 copies of that client instead of 1,000 clients, right? So that's one possible attack. Another is we can just take a client and ignore it. Or we could create new clients out of thin air by just simulating a random new client. So problems 2 and 3, actually, we cannot protect against, because what we want to do is have a communication pattern where the client only speaks once, where the client doesn't have any identity, and where the client is allowed to drop out. So if the client is allowed to drop out, that's indistinguishable from the server just ignoring that client. Same as for the fake clients. If we don't want identities, then we cannot distinguish between a maliciously generated client or like an honest client. So what we're focusing on solving then is including the same client multiple times. And again, we do that by using the zero knowledge proofs that we already have. So in more detail, the client samples a random nonce or a random ID and uses that in their proof of knowledge. So think of it just hashing it into the Fiat Shamir transcript. And now what the server has to do, it's basically proving to the committee, which we call the verifier here, proving that it did not include a zero knowledge proof with the same nonce twice, right? And to do that in a distributed fashion, what the server does, will build this aggregation tree. So it has homomorphic commitments to the ciphertext. At each inner node, we will have the sum of these commitments, and at the root, we will have the final ciphertext that it asks the committee to decrypt. And so what now each committee member just has to do is take a part of this tree or take like an interval of this tree, check that all the IDs that are in the zero knowledge proofs here are sorted so that we cannot like shuffle those around and include them multiple times in different parts. And then check that all the proofs go through and that the commitments indeed add up correctly. And we can instantiate that with like O of square root n committee members, and then each of them does O of square root n work. So that means that the efficiency requirement that we had, that each committee member does work sublinear in the number of clients, that is still satisfied. I'm leaving out the log factors here, but yeah. Okay, so can we actually implement this? So how does this look in practice? And here on this plot, we compare it against Flamingo, which was like the closest committee-based work that we had before, using different settings for our protocol. So in particular, we have two variants. One is like against a malicious server. The other one is against a covert server, where we have some probability of the server getting away with cheating. And then we either take a constant size committee or we take the square root n size committee. And you can see that in particular for large numbers of clients, the square root n size committee pays off, and the total communication per committee member is sublinear in the number of clients. So one question that now in the end you might have is, wait, you were talking about this random oracle in the beginning, and I don't see anything about a random oracle here, right? So the reason is I left out a little bit in the full protocol because it will get just a little bit more complicated. So what we do in the actual implementation or in the actual protocol is we don't encrypt the vector directly, but instead we mask it with the output of a random oracle, right? So we have a seed RI, so each client I has a seed RI. We expand that using a random oracle, and then we add that to the input before encrypting it using our KHA scheme. So now, of course, we also have to have a way to remove this auxiliary mask in the end. And for that, we have a second public key encryption scheme that, again, is implemented by the committee. So there are two possible ways you can think of how to do this decryption in the end. The one we have in the paper is just that the committee at the end of the protocol reveals the secret key to the server. And again, like the only reason we need this is for a technicality in the simulation proof. And we would conjecture that using like a game-based definition, you could probably get away without this random oracle in here. And an alternative is if you really want the simulation-based security and you want like a multi-round protocol with reusable setup, then what you could do is basically have the committee also decrypt these seeds from the clients. That means the total committee work is linear again in the number of clients. But we saw with the verifier how we can split that up into like square root n size committees, and then each committee member again has sublinear work. Okay, so now I'll give back to Arish.
You. Okay, so this is one-shot private aggregation. In case you didn't see the title slide, you can scan the QR code. I had to make it fancy, put a QR, put a JP Morgan Chase logo there inside. But anyway, so federated learning, as I was talking about, is in the clear. The clients do what it's supposed to do, send their model updates, right? But then what really has happened in the prior work is that you really require multiple rounds to ensure privacy. And so that's was sort of the motivation, at least with which OPA was conceived was that you really want to bridge this gap between the fact that in the clear, you can do it in one shot, whereas when I actually have to do it with privacy, there's been multiple rounds. So this is sort of the OPA, our main contribution is as the first protocol to ensure it's single communication per iteration for all clients. This is including the committee, even malicious security settings. And there's no state that needs to be held across iterations. And we really don't need any kind of special purpose PKE or setup. We only need generic PKE to encrypt to the committee and PKI for the clients to authenticate. This is specifically to prevent some server from maliciously crafting inputs. Okay, so how do we actually build OPA? Is that we build it using this notion, we have proved that something is leakage resilient. I'll explain why it's leakage resilient. And then we use a seed homomorphic PRG and then pack secret sharing. We instantiate the seed homomorphic PRG from learning with rounding and ring learning with errors, ring, but other one. So how do we do it? So what really happens is that I will first take, oh, it works. Great. So the client has its weight, that's W1. X1, think of it as a seed. So I'm expanding this using a PRG so that now I can make the seed to be much shorter than the input length. And I will use it to mask it. So this is what's being sent to the server. The server can simply add it up. And because I use a seed homomorphic PRG, it means that the G inside and the G outside, I can take it out. So G of X1 plus G of X2 plus G of X3 is nothing but G of X1 plus X2 plus X3. And I just add the mask. So now somehow the server just needs to get the sum of the masks. So how does it work? Yes. Sum of this seed alone, that's all it needs. So what I do is I just secret share it and send it to the committee. And this committee can be just peak client devices. So that's why I just put a phone. Right there. So I secret share this and I send the share of X1, share of X2 sent to the committee, share of X3 sent to the committee. And because Shami secret sharing is additively homomorphic, I can actually simply add up the shares and send it back. Add up the shares and send it back to the committee. And the committee can reconstruct. And what it gets is the sum of X size. So now it knows the sum of X size. It already needs to just remove it, expand it, and then remove it, which is what happens. But now this is where the cleverness, the trickiness comes in, because the server actually learns the sum of the inputs, some of these, the seeds that's being used. So you really need some notion of leakage resilience because otherwise, because there's some leakage happening in the seed of, in the knowledge of the sum of the seeds. So we show that the seed homomorphic PRG, at least the one from learning with rounding and ring learning with errors, are actually leakage resilient. We also build it from class groups, but actually it's not leakage resilient enough. So we just throw it in as an independent result. But the main thing is that we really need a leakage resilient seed homomorphic PRG. And I can marry it with a pack secret sharing or any secret sharing that's additively homomorphic. And that's it. And implicitly what's really happening is that a key and KHE that was used in Willow is instantiated by the fact that I have a seed homomorphic PRG. That's it. So then I guess I didn't realize the slide was still there. Okay. But anyway, let me go on to the malicious actors. Because the malicious server, you really know the standard approach is to use a double masking, which is what Philip touched upon, where I first use this random oracle model to expand another seed, etc., and because of the impossibility to resolve. But which is just pretty standard, nothing interesting there. And we also throw in this malicious clients, because what if a malicious client sends inconsistent information? For example, inconsistent secret sharing, because there is secret sharing that's being used. And then we use this technique of the scrape test to ensure that the committee's verification is actually much smaller. So I just, the committee receives a commitment to the share, it decrypts and sees if it matches. Otherwise it will complain. And we get only malicious security with abort. And I think there's the follow-up paper which we have in CCS this year. We actually do this thing where we get malicious clients are removed, and then you can get guaranteed output delivery, but that's slightly separate. And we have more experiments in the paper where we show that our server and client running time is pretty good, and it scales decently well when we go for larger and larger clients. There's more in the paper because we were submitting it to CCS and stuff, so they like a bit of graphs everywhere. So what are other contributions? We extend OPA to support more complex aggregating functionalities for FL applications, because I was talking about this averaging, right? Averaging is great, but it's terrible for non-IID data. So if I don't assume that every client has a very similar distribution of data, it has been shown that the model that's being trained eventually is actually terrible. But the thing is that there are several algorithms that's proposed by the machine learning community to up to basically bypass this. One is called the Fed OPT, and that's instantiated with different ways. But what we really observed was that, you can essentially what really happens in all of these approaches is that the server gets the average, and then it does some post processing of the model before the model is updated. So I can just use plugin OPA immediately. So you get this OPA nice plugin, and now OPA now can support other better non-IID distributions primarily. This was also a comment that we received from the ML conference, so therefore we had to throw this in because they got really upset that we weren't discussing the non-IID case. But anyway, what is the conclusion? Before I let you go to lunch, remember to break a couple of plates or two. We introduced OPA, the first protocol where clients speak once per iteration. Even the committee members speak once. And we use a committee of ephemerally chosen client that can change from iteration to iteration. And this is a strictly weaker computation that's required than a server. And we show that it can be extended to be secure even if all the committee members collude, which is just an interesting extension. Our building blocks are generic. We use additively homomorphic secret sharing plus a seed homomorphic PRG. And we build new seed homomorphic PRG from ring learning with errors and class groups. We also have a distributed key homomorphic PRF. And we have extension of the secure aggregation protocol now support multiple more better tailored cases for federated learning. And we also have malicious security with Abort. So, and that brings us to, I guess, do you want to do this together? I guess my voice is loud enough, it's okay. So this is what we asked our favorite AI that chose to remain anonymous. So this is some conclusion comparison between OPA and Willow.
Sure. Yeah. So this AI decided that OPA, in fact, has only a single round of participation for the stateless decryptors, whereas in Willow, we need state for the decryptors. But that means that clients have to communicate a little bit more in OPA, whereas in Willow, the client upload is independent of the committee size. So that makes OPA maybe more suitable for federated learning settings where we don't have a lot of clients, but instead we have huge vectors. And Willow is more useful for like millions of clients and simpler statistics like histograms. Caveat of these analyses, of course, well, first of all, it was done by an anonymous AI, and second of all, that we did not have any concrete numbers to put these things on, so it's more like an asymptotic, conjectured comparison.
And the AI may or may not be unbiased. Okay, that's the. Any questions?
These are QR codes that link to the two papers.
Any questions? Wow, everyone wants lunch. Break, seriously, a plate or two, and say, oh, how do you do it? Because it's important. Okay, we need to celebrate the paper finally.
All right, let's thank the speakers again, and we'll adjourn for lunch.